Yeah, thank you so much for the kind introduction. Welcome to my talk, Building with Robots, or How Humans Can Build Together with Robots. So my name is Kathrin. I lead the Professorship for Digital Fabrication at the Technical University of Munich. And I will share with you some research today which is not very mature, but I would be able to or I would be happy to discuss like preliminary concepts with you. And I think maybe this round is a good occasion to kind of expose it to some discussion or discourse. This is an image that is often shown in our field, our role model, kind of full automation. In building construction, role model would be classical manufacturing industries, such as here automotive sector, where the production chain from design to final assembly is largely automated, and we often have put this picture as sort of what we also want to achieve in building construction. However, we learned over the years that building construction is not directly comparable to the classical manufacturing industries. There's manufacturers. The built environment is intertwined with the material reality of the society and geographic locations to which it belongs. No? So it's more difficult to centralize, to streamline. It's kind of dependent on availability and supply chains, as we have heard yesterday from Mariana, on legal framework conditions, which are heavily kind of inflicting on it, as well as industrial practices, technologies, and skills so far. So the research in my team tries to take a more nuanced take on robotics and automation for building construction. Also, big words: robustness, redundancy, resilience, something that kind of is in the undermath of projects that we are doing. Trying to understand how can we flexibilize processes, how can we make them not optimized but more redundant and resilient. And what I mean with this, I will show with a range of projects that are dealing with bringing humans into robotic fabrication procedures. So I'll start this lecture with one very recent exploration that we're doing. It's called Unbuilding. So it actually looks into how to take buildings carefully apart. It's a PhD topic of a researcher in my team, Begüm Saral, and a collaboration with Stefan Leutenegger, professor for machine learning and robotics. And the project started by observing typical end of life for building structures today. So I think we have also seen this multiple times. So construction demolition waste makes up to a majority of the gross waste. Now, specific number in Germany, but I think this is a problem worldwide. It's a lot of building material that turns into construction waste and never gets another chance to be part of our built environment. And current linear approaches involve demolition with destructive machinery, resulting in large amounts of construction waste being discarded in landfills. So this would be the linear approach. It's today preferred because it's labor and cost effective. However, it undermines the potential for reintroducing them into the cycle. So what if we would deconstruct our buildings with the same care and the same sort of deliberateness as we construct them? No? So, and how could that help to reclaim materials in their entirety through disassembly without actually destroying them? So, and this is very challenging, not only because of the robotic processes, but generally because our modern building technologies, our buildings are sort of built very complex. They're glued, mechanically connected, and so on. So it's not very simple to do that. And also when we look back into history, actually, let's say before the industrialization of building construction, this was, of course, common practice, salvaging material and reusing them, especially in masonry and brick construction, has been a very prevalent method. And the question is, how can we learn from this? How can we reclaim this? And how can robotics or digitization also help us in doing so? So we have set up a very, very simplified case study. So starting really from very simple sort of conditions. where we look into brickwork disassembly as a very simple and maybe also pre-industrial case for taking buildings apart. And then maybe later on also to see how we can basically take that back into the cycle. So we have set up a very, very simple case with dry stacked brick. So without any mortar bonding, so just the mere brick. So in contrast to a typical assembly scenario, or when we think of construction, we have a digital model, we have a building plan, we make either people or robots construct buildings at very specified locations that we have previously determined in plans. When we disassemble, we actually have to start from a place where we have to work with found situations and then derive actions basically from these found situations. No? So something that later on, maybe, that's a speculation, can be helped much more also with large language models or visual language action models so far. Anyway, we start simple, so we actually utilize spatial AI, spatial artificial intelligence, that focuses on understanding and utilizing spatial information, so geometric and semantic information, enabling robots and systems to comprehend and interact with the physical environment in a manner that mimics human spatial awareness. No? And this makes it particularly fit for working in existing contexts, especially in this kind of found situations, where actually material reclamation and subsequent reuse could be utilized for it. So we have this mobile robotic setup. It's equipped with a hand-in-eye end effector, so a vacuum gripper and an RGBD camera. And it can detect bricks. Okay, so very simple actually. This perception system is based also on learning. So we have created a photorealistic data generator pipeline where we take basically, instead of annotating real-world object poses, which is time-consuming and error-prone, we basically create synthetic data and we learn from that. And then we take this model to basically take the color data from the RGBD camera, which is fed into an object detector. It's segmenting the individual brick objects and then using the segmentation as well as the depth data to really very precisely estimate their pose in space, which could be both utilized in static but also in dynamic mode. This perception or this data goes into the robotic procedures or the manipulation routines, where we have a two-step system. First, to kind of get a knowledge on the whole workpiece. And then actually, so this works a little bit like this. So robot is searching around, utilizing the perception system to determine the position of the workpiece relative to the robot, and then a more streamlined iterative process where individual objects are located, and then some reasoning is happening as to which brick can be taken out of the existing structure. No? So also this is kind of not very fast because we are also like kind of developing the system, but here you can see the detection of a single brick, and the pose estimator is triggered to retrieve the poses of the bricks in its vision. And then upon detection, found bricks are added in real time to the digital twin, which serves to track and store the detected and disassembled bricks in their as found locations. If the robot assesses whether it can reach a brick, it moves to the estimated pose. Then a planning request is initiated to a motion planner, and the most effective trajectory is chosen to be executed. No? So the robot arm moves in Z-axis utilizing force control also to then grip the brick until a contact is made, and then relocates it. So very like subsequent steps that are necessary to do so. No? And then this process repeats as more bricks are detected and localized until the robot collects all the bricks within its static reach. So during this process, within the planning scene, Bricks are also systematically removed from found locations and added in a storage. So now this is on the back of the robot. But as as this loop continues, basically until nothing is reachable anymore, then we relocate the robot, which is done manually, where we use a fiducial marker to localize, and then basically by relocating it multiple times, basically this whole wall can be disassembled. So following this methodology, a digital twin is generated as a result of this process. So actually the reminiscent of the building is the digital model, even when the physical structure itself no longer exists. No? So this is something actually very nice conceptually, that we kind of build this up as we take a building apart. Potentially this would be possible to be reused for if you want to reconstruct it in the same way. Some technical aspects. So since we used the first time sort of machine learning models to classify the bricks, we learned that it's extremely robust, and it's also possible to basically not also to extend basically the catalog, not to classifiable objects, different sizes, different colors. So we are not very constrained in that. There's of course outliers in the pose estimation, but even that is extremely precise as compared to previous methods that we have used. And there's actually a 100% success rate in picking. It's a very simplified case, of course, but it's very nice to kind of see how well these models also perform in the kind of robustness of the system. So we used 5 times to kind of relocate and disassemble, and you can see here processing time is extremely slow, but there's room for improvement. And of course, since this is dry stacked, there's and one material, let's say, it's also extremely simplified, and it's clear that in the next step, we also need to, if we want to get closer to, let's say, realistic scenarios, we need to have more messy sort of situations also kind of to look into. So the next step that we are working on is to create synthetic data sets that also take mortar occlusion into account. So how can you detect objects which are also partially occluded or fully or broken or don't have the same geometry as in the model. And also then the routines as to how this can be done also become more complex, where we are also trying to look into this action models to kind of also derive actions with the help of AI. So spatial AI, or visual perception in robotics and machine intelligence, gives machines the possibility to understand their context, also to reason and to derive actions from them. So in essence, to give a substantial level of autonomy to operate in unknown environments. And typically, this is used to lower the interaction with people, because that means that machines can operate fully autonomy. But what it also enables them, so if there's a high level of autonomy, it also actually increases the opportunities for interaction and also interaction with humans. So this is actually a very nice sort of side effect, let's say, which then allows us to look more into sort of possibilities how to interact and cooperate with robots, mechanical machines, but then also like computational processes, of course, as such. So I would like to step back to a work that I have been doing here at Komatsu Cola Research before I left, augmented brickwork. You will see a lot of bricks, actually just bricks, you can do a lot with them, which we have been doing now 5 years ago in a collaboration with a Greek contractor, let's say. And it looks into a very similar approach, basically hybridizing machine intelligence with traditional manual building techniques. So here also brick tracking without learning, not just kind of line tracking, but it allowed to basically, or what we looked into is how can we use object tracking to not to give robots perception, but to actually use it to instruct people, and to basically use this to give three-dimensional data to people to allow them to build complex geometries. And we have been combining this with traditional masonry, and you can see here how brick and mortar construction, there's very distinct principles of how to manipulate objects. No? In this case, it's really this knocking the brick into the mortar bed, which allows to very finely adjust a 3D location of this object. And we have used exactly that principle to measure that and to translate it into a real-time visual feedback and to real-time visual instructions. No? So you don't only project a digital model into 3D space, but you measure what is in 3D space, and you can update the instructions very precisely and very intuitively in real time. It's very hard to kind of explain that. I think everybody has to try this once, otherwise it's very difficult to explain, but it becomes a very intuitive and augmented process as such. And we have developed and tested this construction of a brick facade for, as said, a winery in Greece, where we have scaled up the system for the construction of, I forgot, 15,000 something bricks. Fields 5 by 5 meters, infill masonry, no, so not load bearing, but kind of infilled into this kind of concrete frames. And we have basically developed a two-person system. So initially we intended a one-person system, but we couldn't. No? So there's actually two people, one that is kind of holding the sensor, holding all of the equipment, and then the second one who is laying the brick, and then also having a turn-taking sort of scenario where the cleaning the mortar joint, bringing the mortar, and so on would be kind of shared tasks. So this is kind of summarized in this video. So you can see here, it's very similar to, if somebody of you know the winery of Grammatica in Gantenbein. So it had the same sort of idea of having sort of individual rotations of brick in space to create some sort of differentiality in the facade. Just that it was not prefabricated, it was built on site, and it was not glued, but mortar was used. And this mortar joint is quite thick, no? So it's like 3 to 5 centimeters, so it's really used to kind of also give the possibility to have some spatial orientation in the bricks. The joints are also not linear, they're like a little bit curved, so to be able to give it more differentiality. And here you can see these kind of little red dots, arrows. And these arrows would indicate where you should knock the brick. No? So it's not just the outlines that are given, but it's kind of given what you have to do. And it's just very, very simple thing, but it has proven to be extremely effective, no? Because it's minimal information at the point, at the time where you need it. And also it's something that you learn over time. No? So it's something that, I don't have the numbers now, but basically constructing one of these infill masonries, the first one took probably 5 times the time than the last one, because it's something that you kind of also learn over time. And you can see here, of course, it's largely sort of dexterous and also crafty. And also, you can see here the 3D model, so we wanted to have like this wavy appearance. And also, while you're doing it, you don't really see the results. No? So you only see it once you like step back and you look at it. So also the trust from the masons came only when they saw the first 2-3 fields together. No? So they kind of understood that what they are doing is actually really having an effect on the larger scale, no? Because it's so small on the parts where you operate. Yeah. And also, like, it's a flat wall, but really it allowed to really give this 3-dimensionality somehow, just by this very little tweak to have the mortar joint a little bit thicker in space. Yeah. So departing from this project where humans are given basically robotic precision and are informed about how and when to carry out building actions, it's very easy to bring robots back into the picture, no? Because they share this digital physical workspace. So we have been working together with Daniela Mitterberger, who I have also already worked with on the augmented brickwork. We have been iteratively creating a few projects, I will show one now, where we try to kind of really look into turn-taking task distributions between humans and robots and what is sensible for humans to do, what is sensible for robots to do, and how can they meaningfully also act together. Of course, there's a lot of research also in multi-robot or human-robot research. The effectiveness comes when multiple agents can do more than what a single can do alone. No? So when there's like some sort of support from each other, and also some sensible distribution, and also what neither humans nor robots could do independently. No? So this would be kind of the objective. So now when we design for human-robot cooperation, we have to take this task distribution into account while designing. No? So the affordances of each have to be somehow known, or the design constraints should be there to know what can be done by each of them. So we can model this. But then also during assembly or doing building, you actually want to allocate the tasks quite flexibly and meaningfully. So how do you, so it's easy to kind of trigger robots, but how do you communicate to people is still a little bit unknown, let's say. And in the research that we have been pursuing, we largely use mobile phones because it's somehow the easiest to take out of your pocket and kind of log in, log out. In this case, or in this specific experiment, we developed, we call it assembly grammar, which means we define not the product but the process. No? So we represent the process geometrically or computationally. In this case, we always have we worked with reciprocal frame structures, so we always have a starting rod. The first one is placed by a robot, the second by a human. And this is kind of turn-taking, kind of growing along arbitrary shapes. So in this case, sort of an umbrella shape. Of course, then you can do some sort of optimization on top of it, simulating what would be the fastest or the most collaborative, depending on how many sort of people are participating or robots are participating. You can take structural stability into account, and also basically take the fabricatability and the structural integrity of the structure at every step. No, you can kind of take it into account at every step. So you don't need to post-rationalize. You have all of these factors already in your form finding or in your form generation. Then we store this information in assembly information models. During building, in the last experiment, we went back to tag tracking because it's so simple. We localized the mobile robot plus the phone to the same markers in the environment. And then it allows us to co-locate sort of multiple mobile phones and robots in the same work area. Here also a little snippet of how this is working currently. It's not very streamlined. It's still very sequential. No? So, and we have to, for instance, robot actions need to be really like simulated and triggered. No? So it's not extremely intertwined yet. But the objective or the vision would be that all of this happens automatically, is tracked automatically, and happens simultaneously. Currently, we can, for instance, preview a robot movement, a robot motion, and then trigger it such that it's executed. Then the human would be informed that the next element should be laid, or the mechanical connectors should be laid, and then the next element should be laid. No? So while one robot is holding, the next one is coming. So it's really, and then of course we would want to have this not that you don't need to follow specific actions, but that you have more priorities where you should continue, but you should be able to basically log in, log out, and participate where it's meaningful, as you would do it also in a normal sort of building construction. And where the digital model is always updated and synchronized, no? So that we always have an updated version, very high resolution at every step of the process. So here's some impressions. This is the first sort of little tiny umbrella structure that we built. This was for the Future of Construction workshop last year. So it's a workshop project. And we have been taking it apart, so it's the same sized element and the same sized connector for these structures. And we have been rebuilding it recently in the RobAch conference in Toronto together with our team and the team of Daniela. In this case, really looking into also stabilization as a design sort of constraint. So the robots stabilize at critical points so that we can also have more sort of freedom in what we can build. And this is the final outcome of this experiment. And we have also tried to do this again, coming back to BRIC, in multiple other scenarios where sort of a distribution of tasks would make sense. Again, this kind of who works with more malleable material and who works with more precision. Very simple distribution, but somehow proves effective for research. So the bricklayer places the mortar, the robot places the brick. Bricklayer knocks the brick into the mortar, and bricklayer cleans the brick. So little installation that we have worked on with masons, like mason school. So also something that we try to do, not to just stay in the sort of academic circle, but really working with traditional craftspeople. And here you can see one craftsperson basically operating in the same workspace. Of course, there's all of these safety things that we have to take into account, so going very, very slow currently. But you really want to have them blending in very naturally into the process. No? This is one visualization of the outcome. And so again, coming back to spatial AI, we can track objects, but we can also track humans. No? So it's really nice to think about how can we take human models into account so that we can have action recognition, action triggering done automatically so that we don't need to do this actively, but that it really becomes a sort of smooth operation. And this is very recently we have started to look into sort of human motion capturing, human action recognition, so that this would allow to track, to trigger robot actions automatically. So in conclusion, to wrap it up, I would like to iterate a few points. So somehow, not very articulated, but we are looking into what alternative vision we can kind of work on as opposed to full automation. So hybrid human-robot work teams that complement each other to increase flexibility, freedom of design, new areas of application. And to some extent sustainability, although we don't know what that really means in that context. And I'll also have one slide for the promotion of Compass XR launch in June 27th, heavily pushed by Daniela. I'm happy to answer your questions. Thank you.
So I think typically when we think of intelligence, especially artificial intelligence, we think about it in terms of sort of like mental acuity and specific sort of logocentric or sort of mathematical tasks. But of course there's multiple intelligences, and I think kind of what you're suggesting is that there is a sort of kinesthetic intelligence that's at play in the segmentation of all of the tasks in these projects. And I was kind of curious if you thought about a sort of more general framework about thinking, like classifying the kinesthetic capacities of the actors in a process, and then thinking about the task at hand and how they might best be coordinated in the realization of that.
Thank you for the question. I think only slowly we start to realize what it means to represent actions as opposed to just geometry, let's say. And what do we need in order to derive actions from an objective? No? So we have been recently, that's why I mentioned this vision, language, action models, because that actually allows us to look at this problem from a completely different perspective. We have only recently started to work with that, no? But basically language models can help us to dissect tasks from an objective, which is now we need to program this very deliberately. No? And especially, let's say, deconstruction gives us a context where even it's hard for us to derive what is necessary to do so, and to access models for that is so interesting, and it's so new also, that this is somehow, where these things also start to somehow make sense now, in that.
Yeah, I mean, one of the most interesting things, or most interesting kind of applications of LLMs, I think, can be taking very unstructured data and requiring or requesting that it be reformatted to a very structured or sort of like coded schema. And I think that's a little bit what you're talking about, is that we have all sorts of, whole history of coded schemas around construction processes. And so how can we take those existing construction schemas and use LLMs to do some sort of like cognitive classification for the tasks? Yeah, it's super interesting.
It's super interesting, yeah.
I had a question about the first project that you presented, the one that is unbuilt.
Unbuilding.
And I got fascinated by the opportunity to create what you call a digital twin of the thing that you're unbuilding.
Yeah.
I was curious if you've thought about the same spatial relationship that you think the robots should have, but then what each brick has in relationship to the overall building. Because I think the moment that you're able to have a brick aware that is standing on top of another brick,
exactly.
you could run other types of, I would call them simulations, or other types of testing. Once you have the building already unbuilt, or while it's in a build, like for example the awareness of physics or the awareness of other things that are much more important than just the geometry of the brick that you're taking out. I don't know if this is something that, if you could elaborate, if you think about it, or
already now we need to take this into account, because basically you can just take the brick off that is on top of the others, and then there's the tree underneath that is kind of locked by that. And that has topological relationships, but also you need to understand them structurally. And for brick walls, very simple, because you do understand what can it. But then there's other structures that it's not so easy to reason for that. No? So in that case, I do think physics are a necessary component. And then maybe in it also later on to run analysis or to run more kind of deliberate assessments of the structure that you have unbuilt, is a huge opportunity. Also to it's very micro level, no? To assess every brick is not what we do usually, but especially in reconstruction it's necessary because we need to assess the quality of materials at the moment. No? So it also allows really to take color, brokenness or any other sort of qualitative feature into account while taking it apart.
It's like a super cool case studies, and super nice to see how this collaboration kind of seems to get towards a point where one doesn't feel threatened by these robots being imminent proximity. I'm just so interested in thinking what are these next steps when one thinks of these kind of robot routines that are very rule-based, like do this, do that, after this, then there's this feedback loop, and on this condition.
Exactly.
And how to combine this kind of world with this very fluffy and probabilistic world of LLMs.
Yeah, exactly.
Because it would be so cool if one would go with the robot into the garden and be like, hey, I want to build an arch. Sure. Point me where you want to start the arch. Just point it with the finger, and you've pointed, and then it goes like, and then you go, go slower, or go faster, or like gentle, right? And it would be able to kind of translate these things into its kind of low-level, rule-based routines. But I'm just so interested in what that communication bridge would need to be.
Yeah, we haven't tried that out very sufficiently, but there's amazing research done by Google DeepMind on these things, not in the sort of not in construction, very generalized, like bring me a cup or something, but prompt engineering allows to then really basically do very complicated things, like go behind to the stairs, sit there for 5 minutes and tell a joke and come back or something, like really things that were unthinkable like a few years back. So I think to apply this or to think of that in the terms of construction and collaboration, cooperation, where this is actually necessary, to interact on a higher level, like complexity, is I think giving so many new opportunities that it's really fun to even think of these.
Brains.
Yeah.
And also this like moment of proprioception is super interesting, right? Like an LLM residing in a whatever, in one of these four-legged robots or an LLM residing, or like kind of driving around in one of these wheel robots that you have with like an arm with like so and so many degrees of freedom, it would need to require a kind of a sense of, at least a simulated sense of self in order to be able to have these kind of interactions. Like now I cannot hide behind the stair because I'm too big. Or
exactly.
These kind of things, and that kind of opens up
completely new basis of exactly.
Machines. Very cool. Thank you.
Yeah, thanks. In the beginning you showed the automotive industry and how we as architects look there to see look how they use the robots in the last few years. But I think right now this industry is facing a lot of trouble, and maybe it does not have a bright future also. So is there maybe some other industry who's maybe in the future like something where architects would look at, or are maybe even the architects themselves, or are we maybe somehow inspiring in the future?
Yeah, I mean, building construction could be this role model of kind of locality, sort of resistance, no, to kind of decentralization. But that's again a very romantic view on it, I guess. Yeah, because also construction labor is unhealthy, dangerous, usually done by low-skilled workers and so on. So, but I do think that there's some, I mean, there's always also a fine line between craft and labor, no? That's also something that we differentiate. And I do think that there's a huge potential of taking this as a blueprint as opposed to kind of, anyway now in a sort of deglobalization attempt, no? Simply because of having to save resources, not shipping materials like from Turkey to Germany or from China to England. There is some sort of like notion of this resistance of a local aspect or local context. And then a building you can just build at that location. No, you will not move it anywhere else. So you do kind of need to have some, kind of local skill set available, people available, and so on. Yeah, so, but that's very hypothetical. I don't want to do any like kind of too much sort of speculation on this. But I do think that there's a huge chance in. Wouldn't it be on the other side so exploitative? There would be a huge chance of taking this also as something that is more, maybe giving us some guidance for future treating sort of the planet, let's say, yeah. But we see, I mean, eventually it's really difficult, I guess, yeah.
Follow up on that question or that kind of reasoning, I think one thing is, of course, the automotive industry and their robots are all very kind of purpose-designed tasks to do different things in the assembly line. Whereas I think the construction industry is much more task diverse, right, and mostly humans. And the sort of parameters for all these different tasks are so different, right? Especially in construction, like the bricks are designed for given hand size, weight, right? So a certain set of parameters from that. Versus that if I'm trying to move a 2x4 lumber or these sorts of things, the calculations are quite different. And of course, I think the future is sort of in terms of being able to capture the task diversity, but unify it under that umbrella that Agostino was talking about, like to be able to address all these like different tasks under one interface. Yeah. Of course, is the holy grail probably in some ways.
Yeah. Yeah. Nice. Yeah. Yeah. Good.
Just quickly as a follow-up of the follow-up. About the presentation, really great explorations through those projects. Thinking about some of your statements, right, like the overall wide research agenda, just in terms of like automating construction. So how do you see that happening in terms of, when I see those projects, also like through presentations these days, I kind of see the realization of individual products. So the way you work with bricks is like making a product, or at least that's how I'm reading that. So I'm wondering if you I can articulate more on that, but I'll ask the question first. If you feel like that it's like in the future it would be more effective to create individual products and then kind of combining them, or you think that it's more like an incremental change for like smaller scale tasks, if it makes sense, that contribute to the construction of anything? Maybe I not completely understand what you mean with product. I don't understand it either. I have short time to think about it.
Do you mean how to generalize from that?
Yeah, I guess. Where you see that those explorations going, if it's like thinking about bricklaying and then I focus on that and I productify that, or as Lisu was saying, right, like the brick is related to the human body and to the hand. Like if we keep exploring robotic fabrication for construction, then we can start building a completely different materials and sizes and all of that.
No, I do think that's a good question, because I mean we have been, or basically the first robots for building construction have been massive. No, they have been like this kind of large scale, one-story, high mechanical monsters, let's say, and they built story by story. No, and this really was largely, I think, inspired by mechanization so far. No, so we have this very large machines and huge. I mean, and it was also meant for a kind of high-rise construction. No, like, but maybe not all of our buildings will be high-rises. So, no, like, it kind of then requires a certain typology. Just one. That's also why I guess they didn't scale ever, because they were not kind of flexible enough. It was something so different. Of course, you need to think of. It maybe doesn't make sense to have mechanical devices that can carry 5 kilos. Maybe you want them to carry 100 kilos, so to do more, no? But in the end, I do think that the more flexible, more smaller scale, but maybe multiplied systems that can adapt to different situations, I do think that there's some, like, kind of maybe advantages to them, yeah.
Hi, thank you very much for your presentation.
Yeah.
I am a little bit curious about how do you see the role of augmented reality in this process, because overall what I understood is kind of this process is trying to get the total automatization of the construction, like leaving the human being on one side, or maybe reducing the interaction of the human being with the robots for the construction. So, do you see the use of augmented reality as one step, like a communication step in the middle, just for maintain this first stage of communication between humans and robots, for then skip the total communication with humans? Or how do you see it?
Yeah, I do think it's a middle step, I mean, we never wanted to work with the glasses because simply they are just so annoying, these kind of things. The mobile phone itself is already more communicative because you do not look at it alone, or you have probably some other people looking at the same screen, and you can have a conversation. You're not like single user experience, kind of shielded away from the rest. And in the end, but it's still a device, that's kind of in a middleware that's in the kind of obstructing. So, yeah, of course, ideally, the necessity would not be there. So that this is again completely taken out of the loop. But that would require really a fully interactive and kind of streamlined, shared kind of environment. And also, really, it's about how you communicate something that is not visible in the physical environment. But maybe it's not even necessary. No, if these other devices are so reactive that it's not necessary, maybe then we can totally get rid of it as well.
Thanks.
Hi, thank you for your presentation. I couldn't not think of the work of Elijah Diasti in Uruguay, and I was wondering if you made any simulations, how it would be like to replicate it, or I was thinking also about the time thing, and then the kind of work if it were made by humans, how long would it take, and how long would it take to do it with the robots, if you have games on it, if you have thought of it. So use it like not to build like common regular houses, but complex structures.
We have not done any calculations on them so far, but and we have also not yet looked into really more spatial kind of geometries. We are working on it to kind of getting there, but maybe in a few years.
Thank you.
Thank you. Yeah.
Okay.
Yeah. Super.
Thank you very much.
Thank you.